Hi, guys. Hey, Carson. Can you hear me, Carson? Guys, can you hear me?
Yeah, we can hear you.
Okay. Sorry. There's a reason the video is not there. Basically, I had a setback yesterday and I was really in pain, so I can't do it from my normal desk. I am sitting in my bed right now doing this. All right. So I apologize for that. I didn't really figure you needed to see my dirty sheets. So I figured I'd save you from that visual. Okay.
That was considerate. Thanks for messing.
How we doing? We doing okay?
Yeah.
I didn't have as many problems with you guys as I did with my other class regarding the submission you had to do for today. Did you do okay with it? Any questions?
With the post lab, the last question about which one we mix it with, the unknown for to see the color change. What I thought it was you mix the unknown with all of the two ones, right?
I'm not understanding your question, Faye.
Hold on, let me get my hold on, I'm trying to find the quiz.
Yeah, I'm trying to pull it up myself then.
It was for this week's post lab.
Yeah. Okay, I'm almost there.
It was the last question. You're given the unknown colorless solution that contains one of the following salts, NaA, NAB, or NaC. In the solution, each salt dissociates completely into Na plus ion.
1 second, Faye.
Okay.
Okay. Substance A, B, and C can all act as oxidizing agents. Is that the one?
Mm-hmm.
Okay. All right. So you know the non-ions. Non-ions are the things giving you the color.
Mm-hmm.
Right?
Which don't have a charge, they're neutral, right?
Yes, correct. I'm sorry, Faye, I'm trying to get, I got 10 people in here. That's what I'm supposed to have. Okay. All right. A, B, and C, the non-charged ones are the ones that give the colors. A, B minus, and C minus are colorless. You're given an unknown colorless solution, obviously contains one of the anions, A minus, B minus, or C minus. Okay, in solution, each salt dissolves. Okay, yeah. But the next, all that's saying is that it dissolves so that you're only seeing the ion. That's what the next sentence says. Na is inert. Okay. Basically, what you do, Faye, or explain your reasoning, and I'll explain why they have the answer they did there. Okay.
I think the oxidation tripped me up because I was thinking react the unknown with, well, first I said the NaA, NaB, and NaC, and if reaction occurs, your unknown is more active.
No. Because when you're reacting it with the salts, nothing's going to happen.
Because it's just, okay.
It's you got a negative ion with a negative ion. There are plenty of electrons around the anions. So there's no transfer of electrons. So there's no reaction that's going to happen when you mix an ion with an ion. Does that make sense with you?
And then I retook it and I thought, then I was like, okay, well then you mix with the A, B, and C, and if there's a reaction, it's more active. Your
Okay.
unknown is more active than what you reacted it with.
All right.
I think I got missed because is the A, B, and C the part that's the color?
I'm sorry, wait. No, it's the opposite of what you're thinking, Faye. If a reaction occurs, your unknown is more active because what it does is it grabbed the electrons. I'm sorry.
So when you're looking at the equation that you gave us for the hint, the unknown would be the x2 or?
The unknown is the y minus.
Okay, that's why I mixed it up in the equation. I was thinking something opposite.
Yeah, it's the y minus that happens because what is happening is you're getting a change of color, correct, Faye?
Mm-hmm.
If you're getting a change of color, that means that the x2 is changed to x minus and the y minus is changed to y.
Okay.
So if that happens, the x ended up ionic, so the x is more active. Your unknown, which is y minus, is less active.
Because it got the electrons taken away?
Because it had its electrons taken away.
Okay, thank you, Professor.
No, no problem. I'm sorry it took that roundabout way to explain that. Does anybody else have any questions? Questions about last week's lab? Pretty much, guys, as I said 2 weeks ago, it's an all or nothing thing. Yes and no. Basically, I found out that they changed the unknowns on me. It's last semester, the unknown was bromine, so I made my color chart to indicate that bromine was the unknown. This time, they used iodine. So basically, if you chose bromide or iodide as your unknown unknown anion, I will give you credit for it. Fair enough? Because I told you to look at my colors rather than the colors that he gave you. Fair enough, everybody? The only way you're not going to get credit on that question is if you guessed chloride. Any other questions about last week? All right. Fairly simple lab this week. Fairly simple. First off, has everybody had the gas laws?
Yes.
Oh, one more announcement. I just want to clarify something to make sure that you're on board with this. I agreed that you would get 9s on all your subsequent lab reports as long as you were just following the general rules on the lab reports, okay? What I said was I wasn't going to go into that much depth grading them. But you still have to submit them. If you don't submit the lab notebooks, then you are going to get a 0 for it. You still have to submit them. It's just that I'm not going to scrutinize them as much as I did before. That was the deal that I made with you. Okay, guys?
Yep, that seemed like a given.
All right. Sorry, I'm trying to find where I'm at. Okay. Everybody seeing the slideshow?
Yes.
All right. Now, I don't know if you saw the video or not, but just to give you an overall visual of this particular experiment, you have a 5-gallon bucket. You have this big long tube that has marks on it. Okay? Into the big long tube, you fill the first 5 milliliters with concentrated hydrochloric acid, and then you make out like you're doing a layer drink. Has anybody ever had a layer drink? you know what I'm talking about? Where they put like the dark liquor on the bottom and then they layer the cream liquor right on top. They do it very carefully, like it doesn't mix. That's basically what you're doing here. You put concentrated hydrochloric acid on the bottom, then you fill the entire tube with water after that. The reason you're doing this is you don't really want to dilute the hydrochloric acid. Eventually it would dilute, but at first it doesn't. So you fill the entire tube with this hydrochloric acid. You then make a hook out of copper, and to this copper hook, you kind of fold a piece of magnesium ribbon on top of it. Then you kind of like put the magnesium ribbon on this hook so that it is in the bottom half of the top half of this tube. You put your finger over the tube, invert it, put it into the bucket. Now, hydrochloric acid is denser than water. So what happens is the hydrochloric acid then will go all the way to the bottom. When it goes to the bottom, the hydrochloric acid sees the magnesium and it starts to react. It reacts with the magnesium to make hydrogen gas. So what happens? If you're seeing my arrow here, the hydrochloric acid reacts with the magnesium, making H2 bubbles. The H2 bubbles get to the very top. Then it starts pushing the water out of the tube and into the 5-gallon bucket. Everybody have an understanding of what's basically happening in the experiment? Any confusion? Any confusion about what's happening?
No.
All right. If you read the procedure, you will notice that there were two procedures. One using 6 molar HCl, the other using 12. There's no real difference in the two procedures other than 6 takes forever to go on. 12 happens immediately. It's a much more exciting reaction. 6, because it's less concentrated, is safer. I generally use the 12 because it reacts right away and I get a much more exciting reaction going. All right, so we let the reaction go until there's no more magnesium. That's basically what happens with the experiment itself. Then what you do is you make your recordings of the measurements. All right, we are dealing with the ideal gas law. Now, the ideal gas law is PV equal nRT. The pressure of the gas times the volume of the gas is equal to moles of the gas times a constant times temperature. I can rearrange that so that I have the constant is equal to the pressure times the volume divided by moles times temperature. Now, if we are using R as a value 0.08206, the value of my pressure has to be in atmospheres. Value of my volume has to be in liters. Value of the moles is moles, and my temperature must be in Kelvin. We're all on a basic understanding here, right? The trouble is, when we're doing this experiment, we can't measure everything directly. The only thing that actually is measured directly is the temperature, and that has to be converted by adding 273 to it. So the first thing we're going to do is we are going to calibrate our Eudio2, because even though it's marked, the markings on the Eudio tube are not really accurate. So what we're going to do is we're going to fill a burette with a certain volume. When I did it, I filled it up to 41.50 milliliters. That result is accurate. I put that 41.5 milliliters into my Eudio tube and I read a new value of 44.00. The experimental value I got to be reading as 38 point, sorry, I've got something in the way here. 38.30, that's my actual experimental volume. My atmospheric pressure was 765.00. This is the pressure that's in the room. Room temperature is 26 degrees Celsius. At 26 degrees Celsius, my water vapor pressure is 25.2 torr. And I weighed my magnesium before I started. That was 0.0331 grams. Okay. Now, when I'm doing the experiment, has everybody has sucked soda up in a straw, right? Okay. How do you get the liquid from the soda into your mouth?
It's like a vacuum.
You suck the air pressure out, right? So you have less pressure in the straw. That causes the level of the liquid to rise. Does that make sense, guys?
Mm-hmm.
Now, I'm sure everybody has also, as a kid, blown into the straw and caused the air bubbles to come out in the soda, right? So when you blow into the straw, you are pushing the level of the liquid in the straw down to the point where it's beyond where the straw is. Now, the key is if you just leave the straw in there without sucking or blowing into it, the level in the straw is equal to the level outside. Does that make sense, guys?
Mm-hmm.
All right, so what that means is that the pressure putting on the liquid inside the straw is the same as the pressure outside the straw. So you have to understand, we're doing this in a tube. The tube has some hydrogen gas in it. So if I can move that tube up and down to where the level on the inside of the tube is the same as the level in the 5-gallon bucket, this means that the pressure inside is equal to the pressure outside. So literally speaking, when I measured the atmospheric pressure at 765.0, when I have the level inside the tube and outside the tube the same, the pressure inside the tube is 765 torr as well. Now, I got to understand what is making that pressure. And what is contributing to the pressure inside the tube is the pressure from the hydrogen. And I'm collecting this over water. So there is a water pressure in there as well by Dalton's law. So if the pressure outside is 765 and I know what the temperature is, I can look at a chart to find out what the vapor pressure of water is at 26 degree Kelvin. That happens to be 25.2. So 765 is equal to my hydrogen pressure plus my water vapor pressure, or the overall pressure, 765 minus the water vapor pressure is going to be the pressure of my hydrogen. Make sense, guys? Are we good with that?
Mm-hmm.
From there, all I have to do is then convert torr into atmospheres by multiplying it by 1 atmosphere over 760 torr. So we got one down. We have 4 values to figure out. We have the pressure down. We good with that? Second thing is the volume. All right, remember, I said I had to move the tube up and down. I had to move the tube up and down so I got the level inside equal to the level outside. When that occurs, I have to read what the value of the Eudio tube is giving me. All right. But also remember that I said the Eudio tube was not accurate. So I have to develop a fudge factor. I put 41.50 accurately measured milliliters of water into the Eudio tube. That read 44.00 milliliters. So my fudge factor is my burette reading over my Eudio tube reading. I put the 41.50, divided that by the 44.00. This gives me a reading of 0.9430. Now, the actual label of that is milliliters burette or milliliters accurate over milliliters in the Eudio tube. So if I want to look at my Eudio tube reading and convert that to an accurate reading, all I have to do is take the Eudio reading, multiply that by my fudge factor. This will give me an accurate volume. So in this case, I have the volume I got when I moved the tube up and down. That was 38.30 milliliters. I multiplied that by my fudge factor. That gave me an accurate reading of 36.12 milliliters. Then all I had to do was convert that to liters by multiplying by 1 liter over 1,000 milliliters. Are we good now? Carson, you look about as bored as you can look right now.
No, I'm just absorbing the information.
All right. Everybody throwing it out there. Are we good with the second reading?
Mm-hmm.
Third reading. This is the gimme. I've got the outside room temperature is 26.0 Celsius. All I have to do is convert that to Kelvin by adding 273.15. Now, I have to figure out the moles of hydrogen. Now, in order to figure out the moles of hydrogen, I need to give you one more piece of information, and that is we've added more HCl than we needed, so my magnesium is my limiting reagent. The formula for magnesium being converted to H2 is Mg plus 2HCl yields MgCl2 plus H2. There's a one-to-one relationship between my magnesium and my hydrogen. So if I have the grams of magnesium, all I have to do is convert that to moles, do the one-to-one stoichiometric conversion, and my moles of magnesium are going to be equal to my moles of hydrogen. So now I have all 4 of my values. All I got to do is solve for R. PV is over NT. R is equal to my pressure I figured out times my volume in liters divided by the moles of hydrogen multiplied by my temperature. I do all this math out and I get an R value of 0.0864. Questions about that, guys?
So will this be like constant? Like every time we do this with different values, we will always get that number?
Yeah, I
James?
thought R was a constant.
Yeah, R is a constant.
So like every time we put different numbers or like do this equation, we'll always get this number.
Yes, James. Not this number. You should, the true value is 0.08206. Okay, James?
All right.
The reason this value is off is it's an experiment. Experiments are going to give you different values. There are error factors. Can anybody think of what an error factor might be in this? Something you have no control over. All right, let's think back. You guys have done this reaction before. Anybody remember what happens when you put magnesium in with HCl? Have you ever felt that? Have you ever felt that reaction? Yeah, this is an unfair question because basically you guys are still in the interface labs. When HCl is added to magnesium, it is a tremendous exothermic reaction. So is the temperature inside the tube going to be exactly 26 degrees, the same as room temperature? It's an exothermic reaction. Temperatures are going to change. Okay? Second thing, do pressures change? We're undergoing it right now, guys. We have, I believe, a low pressure coming in. So the atmospheric pressure is going to change. Basically, it depends upon how quickly the front comes in. That may change very, very quickly. So there are a lot of errors that are involved in this. To be honest with you, there are a couple reasons why I love this experiment, though. One of which is you get much better results than that. I've had people come in with exactly 0.0821. They have done superb on this experiment, and they've come in with dynamite results. The results are very, very good for this experiment. The bad part is that I don't even know. I'm sorry. The other good part is it's exciting. You're literally flipping this HCl over onto the magnesium, and literally speaking, bubbles come up right away. It's exciting, and literally speaking, there's a lot of action involved in this experiment. It's quick, and it gets you out of there fast. So I really do love doing this in person. It's okay doing it in this fashion. But James brings up a point. Do we know what our true value should be?
Of R?
Yeah,
Isn't it?
Yeah.
I thought it was like 0.0821.
there you go. That is the true value of R. When we did our experiment just now, we came up with the value of 0.0864. So since we came up with the value, we can figure out a percent error, which is our real value minus the experimental divided by the real value. In this particular instance, we did that. We came up with an experimental value of 5.24. I would expect you all to put this into your notebooks in the conclusion. This will tell you how close the experimental values were to the real values. You're also doing multiple trials, so you should also be able to do a standard deviation. Not bad, guys. I did that in less than a half an hour. I got nothing more to tell you, really, unless, literally speaking, I'm going to shut this down and try and go into the, okay, is everybody seeing the screen now?
Mm-hmm.
Okay. Blast. Trying to get back to the main screen. Yeah, there I am. Okay. You're going to see that you're going to love this report too, because it's really straightforward. I mean, guys, your last report, I saw some attempts at being 8 minutes or less. This one's going to be a little longer than that, but not much. So you're not going to have to spend that much time doing this. I would suggest doing this right away, though, because there are a little few nuances that you could get wrong doing this. If you do not get an answer, if you do not get an answer that's near 0.08206, go back and check your results because you're wrong somewhere. First question, determine how your UDO2 fudge factor was calculated. Simple enough, guys. All you got to do is take the burette reading, divide it by the UDO2 reading. That will be your fudge factor. Next, all you got to do is report what the information's given to you. What temperature did they give you? What was the mass of the magnesium, the total pressure? I don't know whether he gives you the vapor pressure of water or not. If he doesn't, then all you got to do is Google vapor pressure versus temperature. That should give you a chart. Plug in the degrees centigrade. That will give you the vapor pressure of the water. Question 3, determine the volume in, all right, guys, I want the volume in liters. Convert the temperature to K. I want you to give me the moles of H, and I want the pressure of the dry H2 gas. By this, they mean the pressure of the hydrogen without the water. So you're going to take the atmospheric pressure and subtract out the pressure of the water from that. I also want the pressure in atmospheres. This box, all you got to do is show how you calculated R, and that is it, guys. Easy peasy. Okay. All right, now the other thing, the post lab, 2 questions. Two questions in this. All right, come on. First question, they give you the gas law, they give you the grams of hydrogen, they give you the temperature, and they give you the pressure. Solve for liters. Simple ideal gas law where you change all the labels of all the parameters that you're given and solve for liters. Second question is just a replication of the experiment. Any questions?